So last time we more or less finished discussing quantization of the free scalar field theory, and then we showed that the excitations of that theory essentially give rise to relativistic particles. Okay. And so we also discussed various other things, say Hilbert structure of the Hilbert space, conserved quantities, etc. So at the end we talked about the how to understand the conserved charges. At the quantum level. Okay, so classically, so we have say symmetric transformation means that if you take phi a to some phi a prime, okay, phi a prime, normally we write it in the infinitesimal way, introduce some parameter a, some parameter epsilon, and I can also have multiple symmetries. So for each transformation, say I have epsilon, so alpha labels different transformations, and then so this is the transformation, which can depend on phi a, also depend on its derivatives, etc. And then, so if you have such a symmetric transformation we discussed before, then that generates a conserved current, and it's labeled by alpha. Alpha just denotes different conserved currents. And then, yeah, so it is conserved. Okay. So this is the classical statement. Oh yeah, also Lotzer theorem tells us how to write down such a current explicitly. So we can just write it as, so the current can be written explicitly. Okay, so K mu is the transformation of the Lagrangian density. Suppose under this transformation, the Lagrangian density transform as, say, alpha partial mu, K mu alpha. Okay. So alpha, it doesn't matter. Alpha just label different symmetries. The index doesn't matter whether it's up or down. Okay. And then the zeroth component of the charge, zeroth component of the current, when you integrate over all space, then give rise to a conserved charge. So this is a conserved charge. Okay. And yeah. So now let's discuss. So when you go to quantum level, so when you quantize the theory, and this just becomes a quantum operator, yeah, the whole current becomes a quantum operator, and then Q is also a quantum operator. Okay, so the quantum level. At quantum level, and now Q alpha, because it's conserved, so this becomes time independent operator. We see it explicitly in the case of the, say, Hamiltonian density, Hamiltonian and the momentum. Okay, so we showed explicitly they actually don't depend on time. But at the quantum mechanical level, actually this Q can play a more important role. Can play a more important role. In fact, it can be viewed as a generator of symmetries. Okay, so we can show. We will show the following statement, that if you consider so epsilon, so consider such a quantity, yeah, consider the commutator of Q with phi a, okay, So now let's continue over to here. Yeah, maybe just let me write it here. And that generates minus epsilon alpha F alpha A. Okay? So the commutator of this Q alpha, epsilon alpha with phi A, essentially generates this transformation. Okay, essentially generate this infinitesimal transformation. Okay. So that's why we call the Q alpha also a generator of symmetries. Okay. So this is the statement that I'm going to show very soon. Okay. So before I do that, do you have any questions? Yes.
Conserved currents equation. How can F have an alpha in the upper index when J has an alpha in the lower index? It's not being.
Yeah, just alpha. Don't worry about the location of alpha index. Alpha just label a different current, and just one. Yeah, here we don't worry about its location. Yeah, I just put it up and down just for convenience. Other questions? Yes.
In each supposition, is that a terminal over alpha?
Sorry.
In the supposed bar L is epsilon alpha partial to A mu alpha, is that a sum over all alpha?
Yeah, that's sum over all alphas. So any repeated indices is summed. Okay. So if you only have one, say for example, if you have one epsilon, of course there's no sum. But if you have two different charges, and then this is summed. Other questions? Okay. So so we are going to show this statement, and so this statement is very easy to show in the general case. So let me call this equation star. So let's first consider the case. First, let's consider the sub case that let's first suppose Fa alpha, just this transformation, okay, of phi A does not contain the time derivative of phi A, okay, and also the zeroth component of the k is equal to 0. Okay. So let's consider first a more limited case. Okay. So this the more limited case actually covers many examples. Okay. Actually covers a majority of examples. For example, if you look at the translation symmetry which gives rise to the stress tensor, so this applies to the case I mu, T mu I. So this corresponding to the spatial. So this is the conserved current corresponding to the spatial. So this is the current for spatial translations. When we do spatial translations, then of course this f just given by the spatial derivatives, and then does not involve time derivative. And in that case, the k also does not involve in k0 component is 0. Yeah, just I try to remind myself which you worked in your PSAT. And so for this example, I is the counterpart is the alpha here. Okay, so for each direction, you have a translation, and so this so the alpha of course so I is the alpha here, and the mu is the j mu here. Okay. And also, this applies to the case which for all internal symmetries. By internal symmetries, we mean the transformations don't involve space-time coordinates. Okay. For example, you did in your PSAT the complex scalar field, which you can just rotate by a phase. And that's called internal transformation because that transformation does not involve space-time coordinates. In contrast, when we find the stress tensor, we will do a space-time translation, and that does involve space-time transformation. Yeah, so this corresponding to the space-time transformations, space-time symmetries, and this is the phase is the internal symmetries. Okay, so for all internal symmetries, you don't the transformation will not contain the time derivative. Fine. So in this case, then it's easy because in this case, then we just have the zeroth component of J mu, J just given by the first term by definition is just the canonical momentum conjugate to the A. Okay, so the first factor partial L partial mu phi A, when you set mu equal to 0, so that's just the derivative with respect to the time derivative of phi A, and that by definition is just the canonical momentum density conjugate to phi A, and then you have F alpha A. Okay, F A alpha. Okay, good. So let me just make one comment on this expression. So this expression, of course, classically, you can write whatever way you want. But quantum mechanically, there's a very important subtlety because this typically will involve phi, okay? And then this is momentum, and they don't necessarily commute. So this is the field theory version of so-called the ordinary ambiguity, which it's already in quantum mechanics. Okay, in quantum mechanics, when you go from classical, even it's already in the non-relativistic quantum mechanics. When you go to classical mechanics to quantum mechanics, and then there's an issue how you order operators when you have x and p at the same time. Okay, so here you also have potential ordering ambiguity. You have to pay attention. Often such kind of ambiguities can be resolved by physical considerations. Okay, so we will see some examples in a little bit. Okay. So now let's just imagine there's some ordering we have chosen. And now let's look at this commutator. Okay, so we can just write down the definition. So this is just integrating over all spatial moment, spatial direction, epsilon alpha, and then we have pi a, f a alpha, phi a. Yeah, let me just. Sorry, here let me call phi b because the phi a now they are different. So these two indices are summed. Okay, so like let me call them b, and then you have phi a here. Okay. So now you can use a commutation relation between the momentum density and the phi. So we discussed in general that so we discussed the scalar case. But in general, you have this commutation relation, which is delta 3. Say if this is the x, and this is x prime, and then this is x minus x prime, okay, and delta AB. Okay, so each one it only have a canonical conjugate momentum with its own momentum. Okay, if they have different fields, then of course. Yeah, so yeah, you have that. And now if you use this, okay, so here is x. Yeah, let me call this prime and this to be x. Okay, sorry, I should label more explicitly x here, and then here will be x. Okay, and so here is x, and here will be x prime. Yeah, sorry, I didn't leave myself enough space. Let me just rewrite it. So this gives me d3x prime epsilon alpha. Then I will have this pi a, then x prime f alpha a x prime, and then with commutator with, yeah, not called b. Sorry, alpha is down upstairs. B, and then phi x. Okay? Okay. And yeah, so we can evaluate this, say for example, all at t equal to 0. So I suppress the t. Okay. And then, yeah, and now you can just trivially use this commutation relation, and then this just gives you minus I epsilon alpha f alpha a f a alpha x. Okay, evaluate at x. Okay. So that just confirms that expression. Okay. Confirm expression. So this is not satisfied when you have time translation. Okay. So for time translation, so first, any questions on this? In this simple case, yeah, the idea is very simple. It essentially just the first term propose you to the momentum, and then momentum conjugate to this, and then you just take that. Okay. Yes.
The term with the commutator is f and phi because of our restriction.
That's right. That's right. Yeah. So if there's no partial zero, there's no time derivative here, means there's no momentum here. If there's no momentum here, then this will commute with this one. Yeah, no matter it's in here, it's always commute. Yeah, a very good question. Yeah, I forgot to mention this point. Yeah. Other questions? Okay, good. So now the special case is that if you have time translation, okay, when you have time translation, for example, one example is the Hamiltonian density. H is equal to pi a partial t phi a minus L. Okay, so the L here for the time translation, L is the analog of the k, and the partial t phi a is the f here. And then here is the pi a. Okay, so here you also have time derivative. Okay, here you also have time derivative, and so this by itself is also a pi. Okay, and then L may also contain time derivative. So L is the k0 here. Okay, so in this case the k0 is non-zero, and which is equal to L. And so in this case the conserved charge is just H. So in this case, our general argument here don't apply because now you have pi here also, and you may have a time derivative here also. Okay, so the story is more complicated. But this case we know trivially is true because it's by definition H acting on any field. Okay, is minus I partial t phi a. And this is exactly time translation, a transformation of fields. Okay, so in this special case, this equation is also satisfied. Good. Any questions on this? Okay, so this is just follow from the Heisenberg equation itself. Okay, and now you should just understand this equation. So H now can be considered as a symmetry generator for time translation symmetry, and when it acts on the field and generate the time translation. Okay, time translation just infinitesimally just a time derivative on phi. Good. So these are infinitesimal transformations. But now, starting from here, you can actually obtain finite transformations on the field, also using Q. Okay, so we can generate finite transformations. So let's consider, say, U lambda alpha. So lambda alpha just some parameters. Let's consider this quantity. Okay, now I exponentiate this Q. So Q is the operator, and lambda is just some numbers. Okay, lambda is some constant parameters. Okay, and again the alpha is summed. Yes.
So I understand how this flows from like the Heisenberg equation of motion, but here, how would you evaluate this commutator, not knowing the form of LU, but because he said it can depend on like time derivatives as well.
Right.
So
Yeah. Here, just this general argument don't apply anymore. So in this case, you really have to. You can check it explicitly. You can just write down the explicit value, explicit form of H, and then work it out explicitly. But you don't have to do it because we know this has to be true, but just by self-consistency. Because we solved the Heisenberg equation. Yeah, because when we quantize it, essentially we are solving the Heisenberg equation. Yeah, but you can check it explicitly yourself that this is true. Yeah. Good. So here, so lambda alpha here just some collection of finite transformation parameters. Okay. So this can be used to generate the finite transformations. Okay, so if you act U lambda alpha phi A and U lambda alpha dagger, and then you just get phi A prime. And now this is a finite transformation, finite symmetry transformation of phi A. Okay. And when you expand, when lambda alpha is infinitesimal, and then you can just expand this exponential, then the leading term becomes this one. Okay. The leading term becomes this one. And yeah, so when lambda alpha equal to epsilon alpha goes to 0, and this equation star, and then star reduces to star at the leading non-trivial order. When you expand the exponential, okay. So this can be done in general just. So the reason this is true, without even doing any calculation, you can just imagine you can build this U, this finite transformation by infinite number of infinitesimal transformations. And the so when you build them up, and then you will just generate the finite transformation. Okay. So you already worked out the example in your P set. So you already worked out the example in your P set that if you consider HT minus I PI XI acting on phi 0 minus IHT plus IPI XI, and then this just gives you phi TXI. TX. Okay? Just give you phi TX. And so this is, so here HT minus pi xi is our lambda alpha q alpha here. Okay, so alpha here runs 0 and I direction. Okay, so in the 0 direction, the t now is just some parameter, and the lambda alpha equal to t and the minus xi. Okay, and then q alpha is just and q alpha here is equal to t xi. Let me just do t xi, and the q alpha here is just h minus pi. Okay. Okay. Good. So this is just an example of that. Okay, this is just an example of that. And also you can consider Lorentz transformation. So another example is a Lorentz transformation. So let's consider, so in your P set you already, so in the Lorentz transformation, the conserved charges, actually there are 6 of them. Okay, mu nu going from 1, 0, 3. Okay, so they are all together 6 conserved charges associated with the Lorentz transformation, 3 rotations and 3 boosts. Okay, and then so when you write the finite transformation, and then you will have 6 parameters. Okay, you have 6 parameters. And omega mu mu, because mu mu is antisymmetric, which you worked out in your P set. So this parameter should also be antisymmetric. Okay, and so they are finite angles. Finite angles. No, sorry, not finite angles. Finite angles and boost. Okay, so essentially they give the parameters for the finite rotation angles and the boost, and so that generates a Lorentz transformation. Okay, that generates Lorentz transformation. And so, for example, you say if you act on u lambda on phi x, and u lambda, you can check dagger on phi x. What you get is phi prime x, and phi prime x is also the same as phi lambda 1 on x. Okay, so here lambda 1x is the Lorentz transformation of x mu with parameter determined by just omega mu mu. Okay, so this capital lambda is just the corresponding Lorentz transformation. Is this clear? Yes.
So you assumed like that you can represent the, I guess the operators that perform these transformations like this, but don't you have to like think about if it follows a Lie algebra such that you can represent it like this, or like the group of transformations?
Yeah, indeed. So here is not say I assume. Here I'm just directly telling you the result. It's just when you build. So if you want to generate the I'm just directly tell you the answer.
It's like the composition of infinitesimal transformations.
Exactly. If you do the composition of the infinitesimal transformation, you will get that. The reason I write down this explicitly immediately, because you should have already seen this in quantum mechanics. Because that's how you do the angular momentum. In quantum mechanics, when you do the angular momentum, the way is the same thing. Here we just generalize it to general symmetries. Yes.
So it was
kind of some similar question, but just that, like, so like this is like a general procedure if you have a symmetry to get the representation on your Hilbert space.
Yeah.
Just through Noether's theorem like this.
Yeah.
But like in QM, we usually just postulate that there's a unitary operator and then demand that the group law holds, right?
Yeah, yeah.
So like, don't we need to show that those things get this, that this preserves the group law, or is that not?
Yeah, yeah. So this is guaranteed. So, I didn't go into that, but this is guaranteed. Essentially, that's how you, this is how you build the Lie algebra. Because Lie algebra is also, the finite transformation is also built up by infinitesimal transformations. And so, so essentially guaranteed, so there is a series of Lie groups and Lie algebra behind this. Yeah, so I didn't go into that. So some of you may already sing a little bit of this when you talk about angular momentum, say in quantum mechanics. So it's exactly the same story there. Yes.
So I know that like rotations correspond to like angular momentum being conserved.
Yeah.
But what is like the intuition for like the thing that's conserved in boosts?
Yeah, it's yeah, indeed. There's no very intuitive way to think about it. Also, it's not that useful. You can define a boost charge. So if you consider all the spatial components, and if you consider all the Ij here, then these are the angular momentum operator, and this is your standard angular momentum operator, which you have seen. And if you look at 0I, and then that was sometimes we call boost charge. It generates the boost, but in terms of the conserved number, yeah, we don't use it in the essential way. Say in other contexts. Yeah.
Thank you.
Yes.
Like, to that question, I think you could think of it like a center of mass velocity. It's something like
What?
Yeah. It just does not give you something additional. Normally when you deal with physical problems, say angular momentum conservation, energy conservation is already enough. Yeah, you normally don't need to use a boost charge conservation, to solve your problem. Yeah, so that's why we don't see this object very often, say when you discuss special relativity or other things. But here plays a very important role that in quantum field theory, this is the operator which generates the boost symmetry. Okay, if you want to do a boost, do a boost in your Hilbert space, that's the operator to do it. Okay. Other questions? Okay, good. Good. Yeah, so in your P set, another example is the phase rotation. Let me just very quickly wrote here. So another example is the phase rotation if you have a complex scalar field. Okay. So there we show there's a loss of charge corresponding to the phase rotation. There's a loss of current corresponding to you can rotate the phase to the field. That's a symmetry, and so that will generate the charge Q corresponding to the first rotation. And then if you have alpha Q, and then when you act on phi, and then you can just check explicitly that will generate the phase rotation in phi. Okay. And we'll generate phase rotation in phi. Any questions on this? Good. So so let's conclude our discussion of the real scalar field. Now we can move to a new part. So before we move to new part, your last chance to ask questions about this part. Okay, great. So now let's very quickly talk about let's very quickly talk about the complex scalar field. And when you consider complex scalar field, we get something new. We get the concept of antiparticle. Okay, so now let's consider the following Lagrangian density. Again, we only consider quadratic, the simplest, only quadratic Lagrangian. But now the phi is complex. Okay. Phi is complex. So so complex is also the same as 2 real. Okay? So you can decompose phi into its real part and imaginary part. And if you plug them in here, and then you find you just get 2 separate pieces. And one is the free real scalar field for the real part, and one is the free scalar field for the imaginary part. Okay, because each one of, if you write phi equal to a plus ib, and here it just become a squared plus b squared, here it's also a plus b squared. Okay? But there's a reason we write so essentially we just get 2 copies of our previous theory. Okay, we just get 2 copies of a previous theory. So you say, oh, then it's trivial. Why should we just consider this? We just get 2 copies of previous theory. But there's an advantage. But there's some something conceptually new when we write in this form. There's an advantage to write in this form rather than write as 2 separate identical scalar field theory. It's precisely in this form this phase symmetry is manifest. Okay, if I just write as a 2 separate real scalar field, and then this phase symmetry is not manifest. Okay, and so here in this form there's a phase symmetry manifest. Okay, so phi goes to exponential I alpha phi, and so you see this. You immediately see that symmetry. Okay, so there's when you write it in terms of real and imaginary part, this corresponding to a rotation between the real and imaginary part. And Okay. Good. And the equation motion is the same because it's just because it's you can easily find the equation motion is the same. Okay, and because it's just 2 copies of your previous theory. Of course, equation motion should be the same. And the Lagrangian density, the momentum density for phi, then it become partial 0 phi star, and the partial 0 phi star become partial 0 phi. Okay, so we can treat phi and the phi star as 2 independent fields. Okay. And then the canonical momentum, say if you take derivative with partial 0 phi, then you get the partial 0 phi star, and vice versa. Okay, so they're complex conjugate momentum and like that. Okay. So we can now write down again. We can just write down the most general solutions. So the basis of solutions is the same. Same set of solutions as before. we just have UK x equal to minus I omega k t plus ikx, and then you have UK x star. Okay, so because it's the same equation, so so the basis of the equation, of course, is also the same as before. Yes.
So if the field is an operator, like doesn't it? If it's an observable, doesn't it have to be Hermitian?
No, the field, it depends. So, yeah, indeed, if it's something directly observable, has to be a Hermitian. But I can have two observables. For example, I can combine them into a real variable. Yeah, yeah, just not necessarily the phi itself have to be directly observable. It's just a field. Yeah, yeah, the field itself don't have to always be observable by itself.
So, and the conjugate momentum also is not.
Yeah, yeah.
Momentum is not a real momentum.
Yeah, this is not the momentum. This is just the canonical momentum for the canonical quantization, right? Yeah. Yeah, this is not the space-time momentum.
And is the adjoint of the field operator the same thing as the star?
Yeah, here we are talking about the classical theory, and then when we go to the quantum, indeed, we will replace the star by dagger. Yeah. Okay, so now we can just write down the most general solutions to this equation. Okay, now we can just write down the most general solution to this equation. So we just, so there's one slight difference from before, almost the same, identical as before, except with one difference. Okay, UK, but here previously we have AK dagger. Okay, we have AK star, say classically. Let me just first write classically. So previously we have these. Okay, previously why we have AK star here when we have a real scalar field? It's because the field has to be real, and then we have always add to its complex conjugate. Okay. But now the difference is that now phi is a complex, okay? And the phi is complex, and then we no longer have the real condition. That means here I can choose another arbitrary constant here. Okay, so this is the arbitrary constant. So by convention, let me just put the star here. Okay, it doesn't matter. It's just the name you call it. Okay. So now the most general solution. Now you have two sets. You have A, which is complex number. Then you have another complex number, which is B. Okay, now you have two sets of complex numbers. Okay, and it makes sense because when you have a complex variable, you double your degrees freedom, and your integration constant also doubled. Okay. So BK independent of A. Okay, so now you have two sets of variables, okay? So you can get the phi star just by taking the complex conjugate of it. Okay, just by taking complex conjugate of it. And then the full set, of integration constant just you have AK, you have AK star, you have BK, and then you have BK star. Okay, so this is the classical story. Okay. So now go to quantum. We just do exactly as we did before. You just promote all those into operator equations. Okay, so you just call this dagger. Okay, just call this dagger. Now you just view every one of them as operators, and now these just become constant operators. Okay, they become constant operators, and now here you also just call them to be dagger. Okay. Okay. And yeah. So now equal time correlation. So still, we have to impose the equal time commutation relation. So now we have to impose the equal time commutation relations. Again, so these should be simple. So we should have phi dagger. They consider as independent operators that they should commute with each other. They're all field variables. And the phi should commute with self. So this is all evaluated at different spatial. Yeah, just to save time, I will not write this explicitly, but all this should be evaluated at the same time by different spatial locations. Okay. Such as all this equal to 0, okay, except the only thing which is non-zero is the phi with its own canonical momentum, okay? So everything else will be 0. The only thing non-zero is phi, which is canonical momentum. Again, should be given by I, delta 3, x minus x prime. And then the similar thing for the phi dagger, okay? Okay, so again, I save effort, okay? So that's what you should impose. So now if you plug those things in, then you can find the commutation relation between A and A dagger. Then you, again, you find and similarly with B, you just get now two infinite family of harmonic oscillators. Okay, previously we have one family, and now you get two families. Okay, and all other commutators vanish. So this part is boring. You can almost guess everything without doing any calculation. Okay. You essentially guess everything without doing any calculation. So now again, you can write the Hamiltonian in terms of AK and BK. Okay, just will be as you would guess them to be. Okay. Just the harmonic oscillator corresponding to AK, harmonic oscillator corresponding to BK. Okay. So and then the ground state again is the state annihilated by both of them. Okay, so this is the vacuum state. And now you can act AK dagger on 0 and BK dagger on 0, etc. Okay? So now we have two kinds of particles. So now we have two kinds of particles. generated by AK dagger and BK dagger now, okay? So now you have two kinds of particles, respectively. And both of them have the same on-shell condition, okay? Both particles have the same mass. They satisfy the p square equal to m square minus m square, okay? So because they all come from the same equation, okay? So now the question is, how do we tell them apart? Okay, now we have two types of particles. They have the same mass, and just by definition, they don't have any. They have same mass. They also have the same spin because they're all spin zero, scalar particles. There's no directions. Okay, and the question is, how do we tell them apart? Okay. So here is this U1 symmetry become useful. Okay, here is this U1 symmetry become useful. So this U1, so this phase rotation. So this phase rotation is a symmetry, and mathematically this is called the U1 transformation. Okay, so this is called normally called the U1 symmetry. U1 is just a mathematical term for phase rotation. Okay, mathematically it's a U1 group. It's a mathematical term So the way we take them apart is by looking at their conserved number. Look at their quantum numbers. Okay, if we look at two particles. So how do we tell them apart? We look at their quantum numbers. And their quantum numbers, so far, they look almost the same because their mass is the same. And by definition, they are scalar particles, and so they have zero, they're spin zero. They don't have spin. And so the only other conserved number, if you want to talk about quantum number, that quantum number has got to be conserved, okay? Because otherwise, if it changes with time, it doesn't matter. It doesn't make sense to use that number to label a particle. But we get one more conserved number corresponding to this symmetry. Okay, so this U1 symmetry. So the Lossor theorem. Yeah, from the Lossor theorem. So this is U1 symmetry. Then tell us there's a conserved charge. So if you work it out, if you work out the Lossor theorem, then you find it's the corresponding conserved charge, which you should have already worked out. So let me just write it classically. So I just write them as phi star. So classically, they have the following form. Okay. So at the quantum level, these become operators. But here there's an operator. But now here there's an operator when we go to the quantum level. Now there's an operator ordering ambiguity now. You see here the phi don't commute with its own conjugate momentum, okay? And so here we have phi multiply its conjugate momentum. And if we change the order, and then we will result a delta function. Okay, we will result a delta function. Okay, and that will give rise to infinite. So at the quantum level, different ordering. Differ by some infinite constants. Okay. So you can take phi. You can if you change ordering them, then you get a delta function. But delta function again is evaluated because these two is evaluated at the same x, and then you get the delta function evaluated at the 0. Okay. So essentially you get the infinite constant. But we can fix this ambiguity. Okay, we can fix this ambiguity by requiring your vacuum state, your lowest energy state, should have charge 0. Okay, because by definition, when you are at the lowest energy, there's nothing there. Okay, it's a vacuum. By requiring the lowest energy state have charge 0. Okay, so that uniquely fix whatever infinite the ordering. So by applying this equal to 0, and then you can show that the Q. So now you can essentially the Q have the following form. Okay, so you can already you may be able to guess the answer. Have AK dagger AK, the minus BK dagger BK. Okay, that's what you get. Okay, so you plug those expressions in. You plug those expressions and it's time derivative. Okay, time derivative gives you pi. You just plug those expressions in. And then again, you find, because this is conserved, you find all this time dependence cancel, etc. And then you get these two expressions up to some constant. Okay, and then this condition requires that that constant must be 0. Okay, yeah, when you write in this form. Okay. You see this annihilates the Q because the A is on the right-hand side of A dagger. So this automatically annihilates the vacuum. Okay. So essentially, this is just occupation number for A, and this occupation number for BK. Okay. So we essentially get Q essentially the occupation number for AK and the occupation number for BK. Okay, so occupation number I just write as N. Okay. Yes?
See how this fixes anything, because if you switch them, you still get the same issue.
Huh?
If you permute them, you still get the infinite constant. So I'm confused why this is considered a fix.
No, when you permute them, then you no longer annihilate the vacuum, right? So that constant will cancel. So only this form, with A sitting on the right-hand side of A dagger, this will annihilate the vacuum.
Right. But, okay, I guess because earlier the line of argument was if you permute them, then you get a delta function. Because you would get the same thing here, right? If you permute them, you also get
No. Here there's ambiguity. Here I don't know how I should order them. Whether I should put phi to the right of pi or put pi to the left to the right of phi, I'm not sure how should I do. Okay, here there's no prescription, and here there's no prescription. But if I impose this condition, okay, then that tells you when I impose this condition, then Q must be of this form. Okay, must be of this form. Of course, when you permute them, it's the same thing. When you permute them, you don't change the operator. You don't change the operator. Yeah, but if you do, say, let's do this order. If you do this order, what you get is this expression with an infinite constant. And then this condition tells you somehow you have to change your order here so that constant is 0. Okay. Yeah, when you write it in this form, when you write it in A and B, and that constant has to be 0. Yes?
So does the ordering ambiguity have any physical consequences? Because besides just things that can be subtracted off?
Yeah, this is a good question, which it's hard to say. So most of the time, you can fix them by some physical environment. As here, you can fix it by some physical requirement, and then you don't have to worry about it anymore. But the ordinary ambiguity requires you try to find such a physical requirement. Yeah, because otherwise, what ordinary should you use? And the process of finding that requirement by itself is understanding the physics. Yeah. Yes?
Done that with when you got the infinite energy in the previous lecture, because now I required the ground state to have like 0 energy and then get some different ordering.
Right. No, in that case, we don't have ordering ambiguity. So in that case, because we just have pi square itself plus phi square and plus phi square. There's no ordinary ambiguity here. And so whatever you get is whatever you get. And if you get infinite constant, then you get infinite constant. You don't have freedom. Yeah. Other questions? Yes?
So I don't also see how like phi and phi dagger is clear that they commute. Like, how do you know that there's no coupling between the fields? Or like, when there is coupling, how do you represent it? And
this is a definition. You say where this comes from?
yeah, like why do you know for sure that it's
Yeah.
0?
Yeah, this is just a definition of the. This is the same. This line have nothing to do with field theory. Only this equation have to do with field theory. This have nothing to do with field theory. This is just quantum mechanics. That different degrees freedom, they commute with each other. Yeah, just x1 commute with x2 in quantum mechanics. Yeah, phi here just phi and phi dagger just it's analog of x1 and x2 there. Other questions?
Every operator commutes with this adjunct in quantum mechanics.
No, it's different from that. Here, here it just means that here you should view them as the variables in the configuration space, and it just in quantum mechanics the variables in configuration space they always commute with each other. Good. So now the key thing is that here is the minus sign. So that means when you look at the commutator between Q and A, you get the A. And if you look at the commutator A with BK, you actually get the minus BK. Okay, you get, yeah, let me just do the dagger because this is used to create the particle. Okay? So if you just calculate the commutator, you just find that. So that means if you look at the states defined by the one particle state corresponding to A and the one particle state corresponding to B, okay, then both are eigenvectors of Q, but here with eigenvalue 1, but this one with eigenvalue minus 1. Okay, so it means they actually have opposite charge. Okay, so K and oh, by the way, so let me explain a little bit of this notation. This K does not mean the magnitude of K. So this K means the because normally our convention is that the 4 vector, say the x mu, we always just write as x. Okay, the p mu we just write as p. So here you should view this as a 4 vector. Okay, so as a 4 vector. Yeah. It just it's a shorthand notation. So k and k bar, then they have opposite charge. Okay. Have the same mass, the same spin 0, but opposite charge. So by using this Q, we cannot distinguish these 2 particles. Okay. So normally we call such a particle, we call in this case, which they are all quantum numbers are the same except some they have opposite charge. We call them particle and antiparticle. Okay, so this we call create a particle. So here we say they create an antiparticle. Okay. So here let me just make a remark without proving it. So in relativistic quantum field theory, you can show that any particle has an antiparticle. Okay, in any quantum field, any relativistic quantum field theory, any particle has an antiparticle. Okay. In the case of the real scalar field, you say we only have 1 particle. In that case, the antiparticle is itself. Okay, yeah. Good. Do you have any questions? Yes.
Could we then write off the fact that Q is conserved just by like the number in the A and the number of B is conserved separately? I'm having trouble seeing why conservation of Q is a non-trivial state.
Yeah, the conservation of Q it follows from the symmetry.
But couldn't I just like the number of A particles and the number of B particles are kind of separately conserved? So
sure.
Could I just read off that Q is conserved from the very beginning?
Yeah, it's a no. Actually, the number of A particle and number of B particle, they're not separately conserved. They can actually, in principle, they can annihilate. Yeah. Here in free theory, they cannot annihilate. But if I consider a slightly more complicated theory, say if they are allowed to interact, and then they can actually annihilate, and then disappear. Okay. And so in that case. But this formalism still works. Yeah. This symmetry is still there. Yeah, so that's why the symmetry is powerful. Also applies to the case with interactions. Yeah, indeed, what you said is correct in the free theory. Yeah. Yes.
So does this mean particles and antiparticles, like the difference between them is conserved, so they work in pairs?
Yeah. Essentially, their property. It means their property almost identical, except they have opposite charge. Yeah. They have essentially, just like real world, we have electron, we have if we have matter, we have antimatter. They have essentially identical properties. And if the world is made of antimatter, everything still will behave the same. And but except just the charge is different.
Between the number of antiparticles and particles?
It's conserved. Yeah, it's conserved. Yeah. Right.
So I guess this is like the electric charge, or is this some other charge?
At least some other charge. So in the case we will go to when we talk about electrons. So in electrons involving more complicated formalism, we have to introduce spin particle with spin. In that case, we also have an electron and anti-electron. And in that case, the story is parallel. And yeah.
So this does not necessarily involve VNN or like things repelling?
No. Yeah, but it's the analog of that. It's the analog of that. Yeah. So the charge here, they can be some other kind of charge. It does not have to be, ENN.
So how can you get like something that's physical, that's conserved, from a symmetry that's not really physical? Like this is not like you can translate in space, or like translating time. This is I don't understand. I don't know how to think about it.
Yeah, that's why we call it internal symmetry. So for things we don't have good intuition about, you just invent a new name for it. And once you get used to this new name, you say, oh, I understand it. It is more or less you getting used to it. And indeed, at first sight, it's not very intuitive because it's not something you can, from your normal experiences, etc. But but this is the, but this is as, at fundamental level, it's not that different from energy conservation. It's just some symmetry, and then leads to some conserved quantities. Yes.
If we have like another conserved charge like Q and not like the electric charge, and like which ones do we call, I guess, particle-antiparticle pairs? Does that make sense?
Yeah, that's right. They can in principle have multiple charges, but the particle and antiparticle, they're always opposite. Yeah, in terms of charges, they're always opposite. Yeah, whatever charges you have.
Okay, but if there's like two different charges that each one can have, you know, like a set of four things, is it a different language?
Yeah, I think, you can have them, but for particle and antiparticle, they're always opposite. Yeah, they can have multiple charges, but they're always opposite. Yeah. Other questions? Okay, good. So this concludes our discussion of the complex field. So we have a few minutes. Then let's do to the next topic. So hopefully. So now let's talk about a concept called the propagators. So again, let's recall in non-relativistic quantum mechanics. So this position vector plays a key role. Okay. So this is the eigenvector of this x, which is the position operator. Okay. So again, I will. Let me just put a hat here to emphasize. This is the operator, and so this is the eigenvector of x, okay? And because this plays a key role, because we need to use this to define the wave function, and then the amplitude of the wave function, the square, give us the probability of a particle at location x. Okay, so this is a crucial quantity. So this language, normally we talk about the Schrodinger picture. You start with psi x at t equal to 0, and then you try to find, let me say, you start psi x, say t prime at some t prime. Okay, you want to find psi x at some t. Okay, so this is the equation of quantum mechanics. Okay, so if you know the wave function at the initial time, and you want to find the wave function at some future time. So now let's imagine we consider this question in Heisenberg picture. So in Schrodinger picture, there's just one. Okay, there's just one eigenvector. Just one set of eigenvectors for x. Okay, for different eigenvalues. But for the Heisenberg picture now, your position operator now depend on time. Okay, so the position operator at different times they are different. So now if you want to talk about the position eigenvector, now you need the label. Okay, so now the position eigenvector need the t label. Okay, this t does not mean that this vector evolves with time. It just this is the label. Okay, this means that this is the eigenvector of position vector at time t. Okay, it just tells you this is the eigenvector at time t. Okay. Okay. And now the question of this z question of quantum mechanics then can be reformulated into a different question. Okay. So in this story, the z question of quantum mechanics becomes the following. What is the value of this object? Okay. Suppose you are in the eigenstate. You are the eigenvector. You are in the position eigenvector. You are in the position eigenstate at time t prime with value x prime. And what's the amplitude for you to go to location x at time t? Okay. Okay. Remember this. This does not involve time evolution. This just corresponding labeling different eigenvector at different time. Okay. So if you know this object, this is called. This we normally denote G. G. This is called the propagator. Okay, this is called the propagator. So if you know the propagator of a quantum system, then you have full knowledge of that system. So you already solved that system. Why? Because, say, let's imagine we want to find psi tx, wave function at time t, and then by definition, this is given by this. So this is the Heisenberg picture definition. Okay, it's the psi overlap with the position vector at time t. And now now we can insert the complete set of states. Okay, I just insert the complete set here. Just this is identity. Okay. And then this object is just G. So you just get G, xt, x prime, t prime, then psi, t prime, x prime. Okay. So if you know, so this just gave you the wave function at t prime. So now if you know this, given the initial wave function, if you know the propagator, you just need to do an integral. Okay, then you find the wave function here. So the full knowledge of your quantum mechanical system essentially is encoded in this propagator. Okay, it's encoded in this propagator. So so now we want to talk about what is the analog of this object, say in relativistic quantum field theory. Okay, in quantum field theory, how do we define a propagator, and what is the analog of the position eigenstate, say in quantum field theory? Okay, and we will discuss next time.